Hi guys, welcome to my all-in-one EDEXCEL GCSE 9-1 physics video. I hope you find it super helpful. I'm not sure how long it's going to be, but I have gone through it and tried to make sure I've hit every single specification point. All my perfect answers flash up, and don't forget, if you want to buy my revision guide, which I have written, containing my perfect answers, you can get that on the website, which will flash up now. I hope you find this video super helpful. I hope your studies are going well. Don't forget to come follow me on Insta, Twitter and Facebook, because I add lots of extra exam tips, extra explanations and just general cool science stuff, particularly on Insta. So I really would recommend giving that a go, and I do go through past papers there too. So yeah, hope you find this video helpful. Let's get started.
So I've opened up my perfect answer revision guide for physics. This is actually applicable for chemistry, biology, but we're going to scroll straight down to this page of the revision guide, which is converting between multiples and submultiples of units. And so this is a list you're going to have to learn in the way that you've learned what the role of the nucleus in the animal cell is, for example. You've got to learn this, and don't forget, because these questions come up all the time. So, as you can see, we've got some prefixes down the left-hand side. So giga, mega, kilo, centi, milli, micro and nanometer. Do notice that these conversions are to convert from the standard SI unit into the new unit you're being asked for. So you need to know that the standard SI unit for time, for example, is seconds, distance is meters, weight and force is newtons, mass is grams, frequency is hertz, speed equals meters per second. So you do need to have a working knowledge of these in order to use this table appropriately. But let's actually go in now and look at a few examples. I'm going to go through some proper exam questions too, and we're also going to zoom in on the length part of this, because actually that's one of the interconversions you'll need the most. So what is 0.2 centimeters in micrometers? So in order to work out what we need to do, we're going from centimeters here to micrometers here. Have a look at these numbers and work out the difference between the two, and you can see that that is times 10 to the 4. Now, it is important that you understand that there are lots more micrometers compared with centimeters. So let's take a different example, one that's probably easier for you to understand. Look at 1 meter length. You have those 1 meter rulers in your lab. You should know that that is 100 centimeters. So you're going to have far more centimeters than meters. And if we actually look at centimeters compared with micrometers, hopefully you can see the same thing, that you're going to have far more micrometers than centimeters, which is why we do 0.2 times 10 to the, and you can see the difference here is 10 to the 4. So we're going to do times 10 to the 4 to get an answer which is 2000 micrometers. Looking now at B, we want 12 megahertz in hertz. So we're going from megahertz to hertz, which is here. Again, there are lots more hertz than megahertz, because megahertz is just a way of writing really big numbers in a nice, easy way. So in order to do that, look at the difference between the orders, and you can see that it's times 10 to the 6. So actually 12 megahertz in hertz is 12 million hertz. In C, we want 9 milliseconds in seconds. So we're going from milli to seconds. There are lots more milliseconds compared with seconds. So you're going to do times 10 to the minus 3 here. And we're using our table to tell us what to do. So 9 milliseconds is the same as 0.009 seconds. Now we want 47 kilograms in grams. So we're going from kilograms to grams. 1 kilo contains 1000 grams, just to give you context. So our number is going to increase in size. So we're going to do 47 times 10 to the 3 according to the table to get 47,000 grams. So in order to be able to answer these questions, you need both the knowledge of this table and to make sure you know what the SI unit is. So these values all along here. And you need to understand if your number is going to get bigger or smaller. And that's why this is quite a difficult task, and it is important that you spend time learning this. Now we're going to take a look at the speed, distance, time topic. So there are some very key equations that you need to be aware of. So you know me, I love formula triangles. So I'm going to have my first one here, which is D at the top, then S, then T. Now you cover whatever it is that you're after. So I'm after distance. So if I cover that over with my thumb, I can see that it's therefore speed times time. If I'm after speed, then we're going to do distance divided by time. And then lastly, time is distance divided by speed. So if they ask you for the equation, sure, use your formula triangles to actually work out what the equation is, but you must write out the full equation to get the mark. Formula triangles do not count. So as you can see on the left-hand side, I've drawn very poorly a distance time graph, and I'm after the speed at point A. So to work out the speed, I know that I need to do distance divided by time. I can read that straight off the graph, so I can see that the distance travelled is 8. The time was 4 seconds, so simple calculation. The speed is therefore 2 meters per second. Meters per second due to the units we can see on the y-axis, which was that distance was given in meters and time was given in seconds. It's important to understand these graphs fully because they could ask you, for example, how long was the car stationary for? So in terms of stationary, you're looking at the flat parts of the graph. So the car is stationary here. Why? Because it remains at 8 meters throughout that time. So how long was the car stationary for? Have a look along here. And the answer here is 4 seconds. This is a different type of graph. So the velocity time graph, or the speed time graph, not to be confused with the distance time graph. So we are being asked to find out the acceleration at point A on the graph. So acceleration is given by the equation acceleration equals final speed minus initial speed over time. And a neater way to write that is A equals V minus U over T. So looking at portion A of the graph, what is the final speed? Well, it's given here. So read across and you'll see that it is 5. The initial speed is given here, and we know that's 0, so 5 minus 0. The time taken was 4 seconds, so the answer here is 1.25. Now be careful with your units, you're looking for meters per second squared for acceleration. Another thing they like to ask you is to calculate the distance travelled. Now this is a longer task, and remember distance travelled is given by the area under the graph. So let's calculate the entire distance travelled by this particular vehicle. So the way I like to do this is by splitting it up. You can work it out as a trapezium, or you can work it out as 2 triangles and a rectangle, which I personally find easier. So I'm going to label them A, B and C. So area A is given by this formula. Well, it's a triangle, so I need to put in a half immediately. Times it by the height of the triangle, which is 5. Times it by its width. Do the calculation, and that will therefore be 10 meters. Area B is more straightforward, it's just a rectangle, so just make sure you're reading the correct lengths. So it's 5 again, this time times it by 3, you get a value which is 15 meters. Finally, area C, we're back to our triangle, so we need a half, times the height of the triangle, which is 5, times the width of the triangle, which is 2, so we get 5 meters. If you add that up, you get a total area of 30 meters, and that therefore is the distance travelled. I've picked out some questions. So question 1, a toy car rolls down a ramp and hits a cushion. The graph shows how its velocity changes with time. So this is effectively a speed time graph. Constant velocity on the graph is shown by. What does the word constant mean? Well, it means same. So where on this graph is it the same velocity? Now you can kind of imagine a y-axis and the numbers going up the y-axis. So it could be something like 0, 10, 20, 30 on the velocity front. So where does that not change? Well, it's obviously going to be the horizontal portion of the line, because at that point the speed or the velocity is going to be the same everywhere. So the answer here is B, the horizontal part of the line. And with these sorts of questions, rather than reading the options through and getting confused, I would look at the question first of all, work out what you think is the answer, and then see if that is an option below. The distance travelled is shown by, well, again, I told you to work out distance, it's the area under the graph line. Let's look at the options, and that's A. The average velocity of the toy car is given by, so remember your equation, velocity or speed equals distance divided by time, therefore that is B. A bus travels along a straight road. The graph shows how the velocity of the bus changes during a short journey. Okay, so we've got a velocity time graph, so again, distance will be given by area under the curve, acceleration will be given by the gradient. Anyway, state the velocity of the bus after 25 seconds. So you're looking up here, the answer here is 6 meters per second. How long is the bus stationary during its journey? Now, I've seen loads of people get this wrong because they think that it's stationary here and here. Well, no, that's absolute rubbish, because look at the velocity, it's 12, so stationary means that it was standing still. So standing still means that the velocity must have been 0, which is just this chunk here, and therefore your answer here is 10 seconds. State the equation linking acceleration, change in velocity and time taken. They're giving you the exact wording, so you want to write it out as they've written it. So you're going to write acceleration equals change in velocity over time taken, or you could have written A equals V minus U over T. Calculate the acceleration of the bus during the first 10 seconds, give the unit, that's worth 3 marks. So we'll have a look back up here and we're looking at this portion of the graph. The first 10 seconds we're looking at the gradient. So that equation was acceleration equals V minus U over T. So that is final speed, which is 12, minus initial speed, which was 0, over time taken, which was 10. So 12 take 0 over 10 is 1.2. The units of acceleration are meters per second squared. State the equation linking average speed, distance moved and time taken. Average speed equals distance moved divided by time taken. The bus moves a total distance of 390 meters during the journey. Calculate the average speed of the bus. So speed equals distance divided by time. Distance is 390 divided by, look on the graph for whatever the time was, and it was 60 seconds. Pop that into your calculator and your answer will be 6.5 meters per second. The bus travels further in the first 30 seconds of its journey than it does during the last 30 seconds of this journey. Explain how the graph shows this. Well, remember that I told you distance is given by area under the graph line, and you can see that the trapezium for the first 30 seconds is way bigger than the one for the second 30 seconds, so therefore clearly the bus travelled further. So for the first mark, state the fact that distance is given by area under the graph, and then for the second mark, compare the two areas under the line, and you're done.
Question 4. The diagram shows some people waiting in a queue at a supermarket. The queue moves forward each time a person leaves the checkout. Person X spends 7 minutes in the queue before reaching the checkout, and the graph shows how distance changes with time for person X. So it's the last person in the queue, and notice that it is a distance time graph. So what is the initial length of the queue? And we're looking for that in meters. So all you have to do is read off here on the y-axis. So read along and you'll see, if my pen wasn't as fat, that it is 6.1 meters. Explain how you could use the graph to work out the number of times person X is stationary. So explain is going to be a very crucial word here, and we also need to work out the number of times the person is stationary. So stationary means that they don't move. So when aren't they moving? Well, it's all the flat portions of the graph. So that's 1, 2, 3, 4, 5, 6, 7. So you're going to say 7 times that they were stationary. And we know this because the flat part of the graph indicates 0 speed. State the equation linking average speed, distance moved and time taken. So out of the way, I'm going to write my formula triangle dst. So therefore average speed equals, cover the s, distance moved over time taken. Part 2, calculate the average speed of person X in the queue, give the unit, don't forget to give the unit. So the distance moved, we know, is 6.1 meters. The time is 7 minutes. Don't get caught out here. I know the graph looks confusing, but it tells us up here that the person spent 7 minutes in the queue. I'm going to multiply it by 60 because the SI unit for time is seconds. So obviously there are 60 seconds in a minute, hence why I'm timesing it by 60. Pop that into your calculator and you'll get a value which rounds to 0.015 to 3 significant figures. And we know that the distance was in meters. I've already told you that I've converted to seconds, which is why the unit here is meters per second. 9.6. By measuring the length of the skid marks, an accident investigator determines that the distance a car travelled between the brakes being applied and stopping was 22 meters. The investigator used a sled to determine the friction. The investigator then calculated that the car decelerated at 7.2 meters per second squared. Calculate the speed of the car just before the brakes were applied. Give your answer to 2 sig fig. Okay, so this is SUVAT. So we're using this equation, which is v squared equals u squared plus 2as. And now it's just a matter of identifying what everything is. So the distance here is s. The acceleration is, well, it's minus 7.2, but that's the acceleration. So that's a. We're looking at the speed of the car just before the brakes were applied. So we're looking for the initial speed, which is u. So that's a question mark. And we know that it stopped. So that means final speed was 0. So just substitute in all these values. So it's literally 0 squared, which is 0, equals u squared plus 2 times minus 7.2 times the distance, which was 22. So 0 equals u squared minus 316.8. How do we get u squared by itself? Well, add it to both sides. So 316.8 equals u squared, and then square root that answer in order to calculate your u. So u will equal 18 to 2 significant figures. I've just double checked the physics equation sheet because I actually knew this equation off the top of my head, so I didn't use it, but they've given it in a slightly different form. And I just want you to see that it does work. It doesn't matter which way around you do it, it does work. So v squared again is 0, minus u squared is what we're looking for, equals 2 times the acceleration, which was minus 7.2, times the distance, which was 22. And then if you pop that into your calculator, you get a value which is, well, it will be the same, won't it? It'll be 316.8 minus, and then because they're both minus, you can get rid of the minus and then square root it and you'll get 18 again. So it does work either way.
We now need to discuss the difference between weight and mass. So people constantly get this confused. They talk about how much they weigh when actually they're talking about their mass, and I'm going to explain what I mean by that. So weight, first of all, is given by the unit N, which stands for newtons. Mass is given by the unit kilograms. And so straight away we can see that they have different units. Now it's worth noticing that your mass is unchanged. It doesn't matter where you stand, which planet you're standing on, where you are in space, your mass will remain the same. So if your mass is 50 kilograms on Earth, it will be 50 kilograms on Mars. And that's because it's really a description of what you're made up of. However, with weight has to take into account gravity. And therefore, when gravity changes, your weight will change. If we look at the equation linking the three, you find that weight equals mass times gravitational field strength. So if you have a mass of 50 kilograms, you're standing on the Earth, which has an approximate gravitational field strength of 10, your weight will therefore be 500 newtons. So this would be the case on Earth. However, on the Moon, if we do the same calculation, we find that although your mass is still 50, your gravitational field strength is hugely reduced on the Moon to, in fact, only 1.6, meaning that your weight on the Moon is only 80 newtons. So this is a huge change. Your weight has drastically decreased on the Moon, whereas your mass has stayed the same. So although in everyday life we talk about how much we weigh, we say 50 kilograms, remember that's inaccurate and that we're actually discussing our mass. And as long as you can use this equation, weight equals mass times gravitational field strength, you'll have no problems.
We now need to look at the topic of force. So just remember first of all the effect that a force has on an object, and that can be that the force changes the object's speed, it can change the object's direction, or it can indeed change the object's shape. You need to be able to list the different types of force, so I've written them out here, and now we just need to have a quick chat about what all of those things mean. So first of all, notice that some of these forces are contact forces, and these are forces which act between two objects that are actually physically touching each other. Non-contact forces is obviously, as the name suggests, when they don't touch. So let's actually have a look at this normal reaction first of all, because that's quite a strange one. This normal reaction force or normal contact force, it's all the same thing. That's when an object is on the ground and it experiences a force which is perpendicular to the surface. And what that means, that's where the word normal comes from, because remember in the light topic, a normal line is a line, for example, drawn like this. So here's your glass block, and here are some normal lines because they're 90 degrees to the surface of the glass block. So in a similar way, the reaction force is felt perpendicular to the surface. And I'll show you an example of that later with a car, so don't worry too much now. Friction is a nice straightforward one. That's when two objects slide past each other, they experience a friction force. So for example, a toy car sliding down a slope will experience friction where its wheels touch the slope. Air resistance or drag, that's to do with objects moving through the air, so it could be a car being driven along the road, and air particles collide with the car, creating a small force which acts to slow it down. The faster the car is travelling, the more particles that will hit per second, hence air resistance increases, and that's why things like cars have to be streamlined to reduce air resistance. Looking at non-contact forces, so let's start with the magnetic force, and that is experienced by any magnetic material inside a magnetic field. Do remember that opposite magnetic poles attract, so north and south poles will attract. Like poles, such as two north poles or two south poles, repel. An electrostatic force is all to do with static charge, so we're talking about the build-up of charge, and it's experienced by any charged particle that's held within an electric field. So a gravitational force, as the name suggests, is to do with gravity, and it's experienced by any mass which is found within a gravitational field. And remember, these masses may be attracted towards each other due to this gravitational force. The easiest example here is the Sun and the Earth. They're both masses, they're both very large objects, and they're held in position due to the gravitational force between them. Weight I've already touched upon. Remember, that is a force acting downwards from any object, and it incorporates both the mass and gravitational field strength. Upthrust, this is when we're talking about water, so for example a boat sitting on water, although its weight is acting downwards, there's the force of the water pushing back up, so it's the equivalent of the normal reaction force, so we call this upthrust, and if weight and upthrust are equal, then we know the boat will float. The nuclear force is, as the name suggests, to do with the nucleus of atoms, or the nuclei of atoms, and it's the strong attractive force between the protons and the neutrons within the nucleus that helps hold the nucleus together.
Remember that force is measured in newtons, and that you'll often see a force diagram, and that's basically an object which is moving, and it will have arrows, and the size of the arrow represents how large the force is. So obviously the larger the arrow, the larger the force. Remember, in your textbook they'll often talk about balanced forces. That is when two forces acting on an object, they'll be acting in opposite directions to each other, and remember that they have to be the same size for them to be balanced forces, and that basically means that an object which is standing still, i.e. stationary, it won't speed up, it will stay exactly as it is. And it also means that an object which is travelling at a certain speed, when it has balanced forces acting on it, will continue to travel at that speed. It won't speed up, it won't slow down. So therefore, if we're talking about unbalanced forces, it makes sense that one of the forces opposing the other force is larger than the other. So if the object is stationary, it will start moving, and if the object is travelling at a certain speed, it will either speed up or slow down. So what are these forces that we're talking about? I'm going to use the example of a car driving along the street to help illustrate this. So you have a car, it's sat on the tarmac and it's driving. So the forward force is going to be the driving force from the engine, and that will be causing the car to either accelerate or just carry on travelling at the same speed. Opposing that driving force will be several other forces. First of all, air resistance, otherwise known as drag. Now what is that? Basically, if you've got a car moving, you've got air whistling past it, and these air particles, they'll collide with the car and they generate a tiny, tiny force which acts in the opposite direction to the direction the car's travelling. And by doing that, they oppose the motion of the car, so they act to slow it down. We have lots of other forces opposing motion, so there's friction. Remember, friction is the force that occurs between surfaces, so friction in this example will be between the car wheels and the road. So remember, it's that friction which is useful because it allows the car to grip onto the road, and in certain conditions like icy conditions, wet conditions, or if the tyres have been too worn, you'll decrease the friction between the tyres and the road, and that can lead to dangerous occurrences like the car skidding. So a bit of friction is important. You have other forces acting on the car. You have weight, remember that's the downward force due to gravity, and don't forget this force, it's called the normal reaction, and that occurs between the tyres and the road surface, and it occurs upwards, so perpendicular to the road. And basically all the normal reaction is it's the force which stops objects kind of being forced into the earth, so it acts against gravity. That's quite a hard one to imagine, but just remember that it occurs at 90 degrees to the surface.
Another physics equation you need to be aware of is FAM. So F stands for force, A stands for acceleration, and M stands for mass. So let's work out the various variations. So force equals, we can see that it's acceleration times mass. If we're after acceleration, cover that up. You can see that it is force divided by mass. And lastly, mass equals force divided by acceleration. Touching quickly on the units, mass should always be in kilograms, force is newtons, acceleration is meters per second squared, so make sure you have that sorted, and we'll look at a couple of examples now. So in this question we're calculating the resultant force required to accelerate a 30 kilogram object at 1.5 meters per second squared. So yeah, we have mass, we have acceleration, we're looking for force, so force equals acceleration times mass. It's a simple expedient of substituting in those values, so 1.5 times 30, which gives you a value of 45 newtons. Question 2. The force on a moving object is 1000 newtons. Calculate the mass of an object if it is accelerating at 2.5 meters per second squared. So we've been given the force and the acceleration. Mass is given by F over A. Our force is 1000 newtons divided by the acceleration, which is 2.5, giving us a value which is 400. Don't forget your units, it is in kilograms.
Remember, when we're talking about terminal velocity, we tend to use the example of a parachutist jumping out of an aeroplane, and you'll often see lots of diagrams of arrows of different sizes. I'm going to try and talk to you about that now. So let's start at the top. We're starting in our aeroplane and our parachutist is looking out and he's about to jump. The moment he jumps, the only force acting on him is weight. So that will cause him to accelerate towards the Earth's surface. Now, the faster he accelerates, the bigger the air resistance, because remember, as he's dropping, he's going to be hitting lots of air, and those air particles are going to be acting in the opposite direction to his motion, trying to slow him down. And the faster he travels, the more particles will be hitting per second. So the overall force of drag or air resistance will become very large. So at a certain point, you will find that the size of the air resistance or the drag will match the size of the weight force acting downwards, and we call that terminal velocity, because all that means is that the two forces are balanced and the parachutist will no longer accelerate, he'll just continue falling at a constant speed, and that is what terminal velocity is basically, neither accelerating or decelerating, just travelling at a constant speed. Before too long, the parachutist will choose to open his parachute because he won't obviously want to splatter on the ground. When he opens his parachute, you see a massive increase in the surface area of the parachutist, and therefore way more air particles will be trapped inside the parachute, and therefore air resistance will increase hugely, and he'll jerk upwards as a result of that, and you'll see that he'll slow down. However, because his speed decreases, that actually causes air resistance to decrease, because if you think about it, the slower he now travels, the fewer air particles will be hitting him and opposing his motion, and therefore he'll slow down. And eventually his weight and the size of the drag air resistance force will become the same, and we call that terminal velocity again, because he's now travelling at a constant speed. Now remember, that terminal velocity will be at a much lower speed than the initial one, and that's due to the fact he's opened up his parachute.
A student investigates terminal velocity. She uses a tall glass tube filled with oil. She drops the metal ball into the tube and the ball falls through the oil. Use ideas about forces to explain how a falling object can reach terminal velocity. It doesn't matter what this question is, if it's someone jumping out of a plane or a ball being dropped into a tube of oil, if it mentions terminal velocity, this is your perfect answer. So first of all, you want to state that the ball has a weight, and that will be its downward force. Acting upwards will be the force of drag. As the ball accelerates, the drag force will increase, and eventually the weight will equal drag. At this point, the ball no longer accelerates, it travels at a constant speed and there is no further acceleration, and this means that terminal velocity has been reached. So that's your perfect answer. Try and write it in sentences. I've written it like that for ease of iPad use. Describe how the student could find out if the ball reaches terminal velocity as it falls through the oil. In your answer, you should include the measuring instruments that the student will need, the measurements she should take, and how she could use her measurements to find out if the ball has reached terminal velocity. You may include a labeled diagram in your answer. So clearly we need to use a timer to time how long the ball falls for, and we need to use a ruler to make sure that the ball is falling over the same distance every time. In terms of the measurements taken, you need to take a measurement of time for the amount of time that it took for the ball to pass between 2 points. You obviously want to work out that distance using your ruler, and then repeat and calculate an average to increase the reliability. To make it even more specific, you could have used a light gate. And then lastly, once you've worked out the distance and the time, you can obviously calculate speed using speed equals distance divided by time.
So we're going to start by looking at circular motion. So any object that moves in a circle has circular motion, whether that's a car driving around a racetrack, whether it's a satellite orbiting the Earth, these both have circular motion. Now, in this topic, we need to assume that they're travelling at a constant speed. However, it's now important that you understand the difference between speed and velocity, because people use them interchangeably, but they're not quite the same thing. Speed is how fast you're travelling, and you can attach a unit to it, such as 5 miles an hour, 10 meters per second, that sort of thing. Now, velocity is a vector quantity, whereas speed is a scalar quantity. And all that means is that velocity has both a size, so yes, you could be travelling at 5 meters per second, 10 miles an hour. However, because it's a vector quantity, it also has a direction, and that's what makes velocity different to speed. They both have a size, 10 meters per second, but velocity has that added thing, which is that it has a direction. So now we talk about an object moving in a circle, and because although it's travelling at constant speed, that object is constantly going to be changing direction, and therefore it has a changing velocity. And the point is, the object's velocity is directed at a tangent towards the circle. That sounds horrible. From maths, hopefully you know that a tangent is just a line that touches the edge of a circle but just goes off at an angle, and therefore an object moving around a circle, the fact that it's constantly changing direction, the point is it will constantly change direction so that its velocity is aimed at a tangent. If that is horrible, ignore what I'm saying. I'm yet to see a question that mentions tangents. Just know that an object travelling at constant speed constantly changes its velocity. Now we need to touch on a separate point, which is that the object's travelling at a constant speed is also accelerating, and that's like, what is she saying? That's so stressful. How can it be travelling at a constant speed but also accelerating? Because acceleration to me means speeding up. No, we need to look at the technicalities of what the word acceleration actually means. Now, acceleration is given by the equation, which is change in velocity over time taken. And like I've just said, although you can be travelling at constant speed, the velocity changes because you're constantly changing direction. Therefore, in acceleration, if you're constantly changing your velocity, you're changing your direction, therefore you must be accelerating. So that is another point they may ask you. An object travelling at a constant speed is accelerating. Let's move on now. Any object that's travelling in a circle must be acted upon by a resultant force. The reason why is because otherwise that object would just fly off in any direction. But we know that that object's just going to keep moving round and round and round, so it must be being acted upon by a force which is keeping it moving in a circle. And we call that the resultant force, and because it's moving in a circle, we call it the centripetal force. Now, this is a question that commonly comes up. The question may ask what three things affect the size of the resultant force or the centripetal force. So obviously, first of all, the mass of the object is going to have a big role to play, because the larger the object, the greater the force needed to keep it moving. Second of all, the speed or its velocity of the object, is going to impact on the size of the force needed to keep it in that place, because the faster it's travelling, the greater its velocity, the larger the force needed to keep it moving in a circle. And lastly, the radius. So remember, that is the distance from the centre of the circle to the edge. The size of that radius is going to impact the size of that force, because obviously if the circle's bigger, it's going to need a smaller force to keep it moving. If that's sounding complicated, don't worry too much about whether it's bigger or smaller. Just learn the three things which affect the resultant force, and that is the velocity of the object, the mass of the object, and the radius of the circle. And it doesn't matter if it's a car driving along a track or if it's a satellite orbiting a planet, these things all have a role to play. Now, sometimes they ask you about the force which is acting on the object, causing it to move in the circular motion. So if it was a car travelling on a track, then that's going to be friction between the tyres and the road surface. If you're talking about a satellite orbiting a planet, then the force keeping it in that circular motion is going to be gravity.
What is the momentum of a bullet of mass 50 grams travelling at 300 meters per second? So momentum is given by this equation, which is momentum equals mass times velocity. This is a nice straightforward example. The only thing to notice is you need to convert your grams into kilograms. We do that by dividing by 1,000 times by our velocity, which has been given as 300, and our final answer is 15. Notice the units, which is kilograms meters per second, and we can see that if we have a look at the equation, well, mass is kilograms, velocity is meters per second, so I'm just shoving them together to get my unit. Getting more difficult now. This is a recoil velocity style of question, but don't worry, I'll show you the easiest way of doing this. So in this example, Emma is standing still and fires a rifle. The bullet has a mass of 0.045 kilograms and is travelling at 350 meters per second. If Emma has a mass of 60 kilograms, with what velocity does she move backwards? So make this comment first of all. Momentum is conserved, which means it doesn't change. And because of that, you can then write this comment, momentum before equals momentum after. And we're going to use this to lay out our answer. So what is Emma's momentum before? Well, we've been told she's standing still, which means that her velocity is 0, times it by her mass, 60. We also know that the rifle hasn't done anything yet, it's going to be fired. In that case, the velocity of the bullet is 0 and its mass is 0.045 kilograms. Looking at their momentum afterwards, so her momentum will be her mass, which is 60, times her velocity, which is x, that we don't know the answer to yet, plus that of the bullet, so that's going to be 0.045 multiplied by 350, and that's a matter of sorting out that equation. So those cancel out, because 0 plus 0 equals 0. We have 60x plus 0.045 times 350 to get 15.75. How do we solve that equation? Well, we take away 15.75 from both sides to get the 60x by itself. How do we make x by itself? Divide by 60 on both sides. So her velocity is minus 0.265 meters per second. In this question, a boy of mass 50 kilograms on ice skates throws a ball of 1 kilogram in front of him at a velocity of 2.5 meters per second. What is the boy's velocity? So, stating the same as usual, momentum is conserved. It's worth writing that, because even if you get the calculation wrong, there tends to be a mark available for writing it. Momentum before equals momentum after. The momentum before is 0 because neither the ball or the boy has moved. The momentum after will be the mass of the boy times his velocity plus the mass of the snowball times its velocity. So cancelling down, 50x plus 2.5, take 2.5 away from both sides. And then to get x by itself, you want to divide by 50, again on both sides. So the boy's velocity is minus 0.05 meters per second, which means he's travelling in the opposite direction. Here's another type of momentum calculation. These will always be answered in the same way. If it's an object colliding with another object and they stick together, then this is the method you need to use. So in this situation, a car of mass 1,000 kilograms travelling at a velocity of 20 meters per second collided with a stationary motorbike of mass 500 kilograms. The vehicles move together after impact. That is crucial. They've effectively stuck together. Calculate their velocity. So as always, momentum is conserved. Momentum before equals momentum after. So let's have a look at momentum before. So what is the momentum of the car before? Well, it's its mass, which is 1,000, times its velocity, which we've told is 20 meters per second. The motorbike has a mass of 500 kilograms, but its velocity is 0 because it is stationary. The momentum afterwards will be their combined masses, which is 1,000 plus 500. So that's both the mass of the car and the motorbike, times their velocity, which is what we're after. So let's start sorting this all out. So that will become 20,000. 500 times 0 is 0, and that becomes 1,500x. To get the x by itself, we divide both sides by 1,500. So x is 13.3 meters per second, so that's the velocity with which they move off at. A car travelling at 20 meters per second collides with a stationary lorry and is brought to a rest in just 0.02 seconds. A woman in the car has a mass of 50 kilograms. What force does she experience? And we need a different equation this time, which is that force equals change in momentum over time. So force is what we're after, so that's x. Now the change in momentum is the initial momentum minus the final momentum. Oh, that doesn't look like what I'm trying to write. So the initial momentum of the woman will be the velocity of the car times her mass, and that makes sense because after all she's in the car. And then we take away the final momentum. Well, it's coming to a rest, which means although her mass is staying the same, the velocity obviously reduces to 0 because the car stops. And time we've told is 0.02 seconds. Use your calculator. So 20 times 50 is 1,000 minus 0 over 0.02. And therefore the force she experienced is 50,000, and the unit is a force unit, so that's newtons. 9. A student is playing a game with some empty tins. He throws a wet cloth of mass 0.15 kilograms at the tins. The wet cloth moves at a velocity of 6 meters per second. State the equation linking momentum, mass and velocity. So that is momentum equals mass times velocity. Calculate the momentum of the wet cloth and give the unit. Don't forget to do the other half of the question. So momentum equals mass, which you know is 0.15, times the velocity, which is 6. When you put that into a calculator, you'll get 0.9. And we can see that mass is kilograms, velocity is meters per second, which is why this is simply the unit. If you can't remember it, just work it out from the equation. The wet cloth sticks to tin 1. The mass of the tin 1 is 0.05 kilograms. The cloth and tin 1 move away together. Calculate their velocity. So I always do this in the same way, which is momentum before equals momentum after. Now we've just worked out the momentum of the cloth, which is 0.9. Because the tin wasn't moving, it must mean automatically that its momentum is 0. And then the momentum after, well, they've stuck together. So we need to add up their masses. So that's 0.05 plus 0.15 times by their common velocity. So let's just do the maths and sort this equation out. So now we simply do x equals 0.9 divided by 0.2, giving you a value which is 4.5 meters per second. The student throws a bigger wet cloth at the remaining tins. The wet cloth sticks to tins 2 and 3 and they move away together. The student concludes, I threw the cloth the same way, so the velocity of tins 2 and 3 is the same as the velocity of tin 1. Do you agree with this conclusion and explain why? So clearly the student is wrong, and that's because the variables haven't been controlled. So the mass of the cloth could be different, the mass of the tins could be different, and the cloth velocity hasn't been measured. So try and use your common sense with this one. 9. The stopping distance of a car is the sum of the thinking distance and the braking distance. Table 4 shows how the thinking distance and braking distance vary with speed. What is meant by the braking distance of a vehicle? Finally, a definition that you just have to learn off by heart. So that's the distance travelled under the braking force, or you could say it's the distance travelled from the moment the brake is applied to when the car comes to a stop. The data in Table 4 refers to a car in good mechanical condition driven by an alert driver. Explain why the stopping distance of the car increases if the driver is very tired. Right, if the driver is very tired, clearly they're not going to be able to respond as quickly, so their reaction time will increase, and this will therefore increase the thinking distance, and therefore, because they've told us how stopping, thinking and braking distance all link, therefore the stopping distance will increase too. The student looks at the data in Table 4 and writes the following. Thinking distance is proportional to speed, braking distance is proportional to speed. Explain whether the student is correct. No, they're not correct, because although when the speed increases, the thinking distance increases by the same factor, the braking distance does not. And then you want to show some numbers here. So you could say, for example, that increasing from 10 meters per second to 20 meters per second increases the thinking distance from 6 meters to 12 meters, but the braking distance increases from 6 meters to 24 meters. Okay, new for this specification is the types of energy. They've kind of changed the naming system, so some have stayed the same and some are new. So we're going to go through each of them in turn, talking about what they mean and some examples. So starting with chemical energy, this is to do with energy stores and it's associated with chemical bonds. And really your examples here are things like food. Remember, food is a storage of energy. The same is true for batteries. Kinetic energy, this is to do with moving an object, so anything that has movement has kinetic energy, so a man running down the road, a bus being driven along the street, they both have kinetic energy. Gravitational energy, as the name suggests, is energy associated with an object gaining height, so anything that has been lifted will gain gravitational energy, for example, a chairlift, a ski resort, an aeroplane, these all have gravitational energy, an apple being picked up, for example. Next up, elastic energy. This is the energy stored when an object is stretched, squashed or twisted. Rubber bands are the obvious place here. Catapults, balloons that have been inflated, anything that you distort and then pings back to its original shape will contain elastic energy. Nuclear energy will become very important when we look at nuclear fission, because this is the energy associated with those reactions. So remember the fuel, uranium-235, which you do need to know, that is a huge store of nuclear fuel and therefore nuclear energy. Thermal energy, as the name suggests, is to do with heat. Anything that has gone hotter has gained thermal energy, so a hot cup of tea, for example. Magnetic energy is new for you guys, and this is the energy stored when like poles are pushed closer together or when unlike poles are pulled further apart. So like poles, remember, is two south poles being pushed together. Unlike poles would be the north and south pole. So just name any magnets here. So just a simple bar magnet, a fridge magnet that you put on the fridge door. These would all count as magnetic energy stores. And lastly, electrostatic. That's the energy stored when like charges are moved closer together or when unlike charges are pulled further apart. So very similar to the magnetic energy. And your example here is hard, but it's things like clouds. Remember when there are lightning storms? There's a huge build-up of static charge. Van de Graaff generators, the same place. Wherever you build up static charge, you will have electrostatic energy. The diagram shows some electrical appliances Which appliance is designed to transfer electrical energy to thermal energy? So we're putting in electricity, we're getting heat out of it. It is clearly the kettle, B. Which appliance is designed to transfer electrical energy to kinetic energy? So again, we're putting in electricity, we're getting movement energy out, which would be the food mixer, A. In all appliances, energy is conserved. What is meant by the phrase energy is conserved? And that is that energy cannot be created or destroyed. It is simply converted from one form into another. The lamp has an efficiency of 20%. Explain what this means. And that means that 20% of the energy input has been transferred usefully. So in the case of a food mixer, 20% of the electrical energy in will have been converted to kinetic energy. Or you could have argued that 80% of the energy input has been wasted. Draw a labeled Sankey diagram for the lamp. Okay, so Sankey diagrams always look like this. Now you do find that a lot of it is wasted, so that's why the wasted energy arrow down here will be much broader than the useful energy. And now let's label all of them. So the lamp coming into that will be electrical energy. The useful energy out will obviously be light energy. And then there'll be wasted energy in the form of heat. Because do notice that lamps get pretty hot. Because we haven't been given any numbers, you can't add any numbers, so don't worry about that.
We now need to look at efficiency. So using this example, a filament bulb was supplied with 80 joules of energy. 10 joules of energy was output as light, the rest was wasted. Calculate the efficiency of the light bulb. You need this equation. So efficiency equals useful energy out over divided by total energy in. And I like to make it a percentage, so times by 100, but that's not altogether necessary. So useful energy out, we know, was the light, so that's 10. Total energy input was 80, times it by 100, so you can pop that into your calculator or just cancel it down like I've just done. So the efficiency is 12.5%.
Right, I'm going to go through some miscellaneous calculations to show how you should be approaching questions if you're not quite sure which equation to use. So my first piece of advice is the moment they tell you to start during your exam, turn over to a blank page and start scribbling out all your formula triangles. So you're pretty much making yourself your own personal formula sheet. Even though that will probably take you about a minute, it will be totally worthwhile because it means when you get to a particular calculation, of which there are many in the physics exam, you don't need to be scrambling around in your brain for the correct one. You just refer to your formula sheet and it should literally just be sitting there waiting for you. So let's have a look at what we have here though. So a student pushes a trolley of weight 150 newtons up a slope of length 20 meters. The slope is 1.2 meters high. Calculate the GPE, so that's the gravitational potential energy of the trolley, and calculate the work done by the student. So what do we have here? Let's identify. Look at the unit. It's a newton, which means it's both weight and force. We know the slope length is 20 meters and we know that it is 1.2 meters high. So gravitational potential energy is given by mass times gravitational field strength times height. We see an immediate issue, which is that we don't have the mass of the object, we only have its weight. So we need to do a preliminary calculation using this formula triangle, which is weight equals mass times gravity. We're looking for mass, so that's going to be weight divided by gravity. Now the weight we've been told is 150 newtons. Gravity on Earth is approximately 10. You could put 9.8, but I'm going to write 10. And therefore you're going to write the mass as being 15 kilograms. Now we're ready to use the original equation. So mass is 15, gravity I've just said is 10. The height, it says that the slope is 1.2 meters high, hence 1.2 is substituted in here. So once I've substituted that in, I get a value which is 180. It's an energy value, so it needs to be in joules. So I've rubbed the rest out so we've got more space. So in B, we're calculating the work done by the student if she pushed the trolley with a force of 11 newtons. So we have work done, we have force. So the formula triangle we need this time is work done equals force times distance. So we're looking for work done. Let's write out the equation. Equals force times distance. The force we know is 11 newtons. The distance, look higher up in the question, she pushed it up a slope of length 20 meters. So that's why we substitute in 20 here. Pop it into the calculator and you know that it is 220. Work done, remember, has the same units as energy, which is why I'm putting 220 joules. Next equation I'm interested in is kinetic energy, which is half of mass times velocity squared. I prefer not to put this into a triangle. I think it's easier if you keep it exactly as it's written, and I'll show you how to calculate the different parts so you can actually see that it can be rearranged easily. In this first question, we're being asked to calculate the kinetic energy of a tennis ball travelling at 46 meters per second with a mass of 500 grams. So as always, write out our equation, which is Ke is half mv squared. Be careful with your units because 500 grams isn't in kilograms, so I'm going to put that into kilograms. So remember, 500 grams is 0.5 kilograms. So start substituting in your values. So it's half times 0.5 times 46 squared. So start to simplify. So half of 0.5 is obviously 0.25. 46 times 46, or 46 squared, is 2116. Times that by 0.25, and that gives us a value which is 529. It's an energy value, so it's in joules. Calculate the velocity of a bus travelling through town with a mass of 5,040 kilograms and kinetic energy of, I'm not going to read this number out, of 527,643 joules. So writing out the equation, Ke equals half mv squared. We know the Ke this time, so I'm just going to pop that in here. I find it easier to answer these questions if I rearrange later. So half of mass, so that's half times 5040. And we're looking for velocity, so we keep that as v squared. The easiest thing now is to work out half of the mass, which is 2,520. Times that by v squared. Now we need to get v squared by itself, so the way in which we do that is divide both sides by 2520. So I'm going to do 527,643 divided by 2,520, which gives me a value of 209.382 ... equals v squared, and then we just need to square root to make sure we just get a value for v. So v equals 14.469. Notice I haven't rounded too early. I'm now going to round to 3 sig fig, so it becomes 14.5, and it's a velocity, which means the unit's meters per second.
So the meaty topic of conduction, convection, radiation, this is all to do with thermal energy transfer, so things heating up, things cooling down, starting with conduction. Now I'm sure you're aware that metals are good conductors. The reason being is due to their delocalized electrons, or you can say they're free electrons, but delocalized sounds a bit fancier. Remember the structure of a metal, you'll need to know this for both chemistry and the electricity topic of physics. So to be honest, it's worth learning. So remember that a metal is made up of positive ions surrounded by a sea of delocalized electrons. So what happens in the process of conduction is that when heat is applied, the positive metal ions start vibrating and they gain kinetic energy. What you find then is that the kinetic energy is transferred from the hot parts of the metal to the cooler parts by the presence of these delocalized electrons. So as the electrons move through the metal, they carry the thermal energy with them, vibrating the positive ions more. And before long, you can see how an entire metal object becomes hot. Now, the opposite of a good conductor is an insulator. And these are clearly going to be poor conductors. So to point out things which are poor conductors, first of all, plastic and wood. Why? Because they have no delocalized electrons, and that is the key point here. Air is also a poor conductor. It is a good insulator, and not just because it doesn't have any delocalized electrons, but clearly it's air, so the particles are going to be extremely far apart. So the chance of them vibrating and colliding with other particles to pass on their kinetic energy is going to be very slim, hence why air is a good insulator. So touching on some exam style questions, so polystyrene, why is it a poor conductor? And that's because it contains little air spaces, and air is a good insulator because it has no delocalized electrons and the particles are very far apart. So you want to link every single object you're given with whether it's a poor conductor or insulator. Next up, for example, a duvet. How does a duvet keep you warm? It's full of feathers or synthetic material that looks a bit like cotton wool. And the point is, again, that it traps air. Air is a good insulator. It's a poor conductor. So less heat transfer will take place, meaning that you stay warmer. So what have we learned? We have learned that metal is a good conductor. Air, wood and plastic are poor conductors. And that notice that solids will be better conductors than gases. Now, convection is a very different type of heat energy transfer. It only occurs in liquids and gases. You cannot get convection in a solid. It literally makes no sense whatsoever. And the key example we always use is a radiator in a house. Now my wonderful drawing comes out. So here's our rubbish radiator, and it's nice and hot because it's got hot water flowing through it. And what happens is that heat causes particles of air above the radiator here to gain kinetic energy. Now, because they've gained kinetic energy, the air expands, which means that the particles occupy more space. Now, because they're occupying more space, it means that they become less dense, so they rise up to here. As they rise, they become cooler. By definition, they become denser, and therefore they sink. And before you know it, a convection current has been set up whereby the process keeps repeating. And that's how a radiator in the corner of a room can actually heat up the entire room. So we've got coffee in here and we don't want it to be getting cold too quickly. So what can we do? Well, I've already said you can put it in a polystyrene cup. Why? To prevent conduction losses. However, because the coffee is hot, can you imagine that bizarrely it will heat the air above the coffee and it will literally set up a mini convection current above the coffee that keeps repeating itself, speeding up the process of cooling down that coffee. So what you want to do here is add a lid, and that's to prevent convection currents being set up. The other great thing about adding the lid is you add a layer of air in here, and remember, air is a good insulator. So you're preventing heat losses by both convection and conduction by adding a lid. Last up, radiation, infrared radiation, which we will have met in the electromagnetic spectrum. It is a wave, which means it is not dictated to by the state of matter. What I'm trying to say here is that it can travel in solids, liquids and gases. And that kind of automatically makes it the most difficult to try and prevent heat losses via. However, there are certain things you can do, and that's all to do with the colour of objects. So do try to remember that white shiny surfaces reflect infrared radiation, which is why in very hot countries like certain parts of Spain, you might see the houses are white. Same is true for Greece, and that's because the white colour reflects infrared radiation. Anyone with dark hair, black hair, you'll notice that your head gets really hot in the sun. Why? Because black matte objects are very good absorbers of infrared radiation. And notice that the hotter the object, or the greater the difference between the object and the surrounding temperature, the greater the rate at which heat is lost. Putting this more into context, so looking at a thermos flask. Am I even going to try and draw this? Oh God. Okay, so that's appallingly drawn, but I can still point out a few things. So, first of all, the most obvious thing here to point out is that it has a vacuum. Now remember that a vacuum is a space with no particles, and we know that both conduction and convection require particles in order to occur, so we say that there is no conduction or convection that can occur within this vacuum. And as always, I'm linking the property with which type of heat transfer it prevents. There are silvered surfaces which line the bottle or line the flask. And the point of that is that it reflects infrared radiation back at the contents of the flask, keeping it hot or keeping it cold. The lid prevents convection currents, which I've already touched upon. And you can say that the whole thing is made out of plastic because plastic is a good insulator. And that's the way you get these answers nice and scientific, is by pointing out the various parts of it and what it stops. So looking at heat transfers within a home, how can we stop all our heat escaping? So first of all, in the loft you can have loft insulation, which contains lots of air spaces. Air is a good insulator, preventing conduction heat losses. You could talk about the cavity walls. So cavity meaning a hole, like a cavity in your teeth. So there's holes within the walls which contain air, again because air is a good insulator. Do notice though that convection currents can still be set up in air, which is why you often find there's also foam, because that solid foam stops the convection currents being set up. You could talk about the radiators now having a silvered surface, and that's to reflect infrared radiation back at the room. And lastly, double glazing. Remember, that's when you have two window panes which trap air between them, helping to prevent conduction. Question 9. The diagram shows how air moves near the coast on a warm day. Explain why air moves. Explain why air moves as shown on the diagram. Hopefully the fact that there are arrows and we're talking about a gas, which is air, and heat, hopefully that's screaming convection at you. So again, this is a perfect answer. You need to rote learn your convection answer. So first of all, state that energy is transferred from the sun, which heats the land. This means that air above the warm land becomes warmer, so the particles gain kinetic energy, and effectively the air expands and becomes less dense. This means that that heated air rises, and therefore there's a space, so cooler, denser air falls in order to replace that warm air, and you've therefore created a convection current which repeats. So this is a convection current answer which you need to just learn off by heart, although they have given you a different scenario to the usual radiator in a hot room, so try and make it applicable to the question. So let's start by looking at the warm land. Initially, the warm land heats the air, and that means that the air has gained kinetic energy, so the air expands, becomes less dense, and rises. So as that warm air moves over the sea, it becomes cooler and therefore denser. So that cooler, denser air falls and replaces that air that was above the warm land, and then by doing so you've created a convection current which keeps repeating itself. Explain how Brownian motion provides evidence that air is made of small particles. So remember Brownian motion, our example here are pollen grains in water or smoke particles. And remember that these large particles move with random motion and they collide with smaller invisible particles. And that's the particles which we find in air.
There's always something about renewable, non-renewable energy. So non-renewable energy is things like fossil fuels, so coal, natural gas, oil. These are things which are running out. They're very good at providing us with energy, but if we carry on using them at the rate we're using them now, we're going to run out. And because they come from fossils, they are not going to be replaceable. So we're turning to renewable energy, things like solar, wind, hydroelectric, geothermal. All those sorts of things are renewable energy, and you need to be able to state the advantages and disadvantages of both. They all tend to have the same kind of disadvantages, which is that they're unreliable. So for example, if there's no wind, there'll be no wind power, no sun, no solar, no waves, no wave power. The only type of reliable energies out there are things like hydroelectric, because that's, remember, when water falls down a dam. That tends to be quite reliable unless there's been no rain. Geothermal tends to be very reliable, but remember there's only very certain places on Earth where you can harness geothermal energy. Places like Iceland, where there's a gap between the two tectonic plates. So places like in England, you won't be able to get geothermal energy. They could ask you how energy transfers occur, for example, inside a hydroelectric power station. They do like to ask you that, because remember, water gains gravitational potential energy because it's at the top of the dam. As it falls over the dam, it will gain kinetic energy transferred into electrical energy to therefore power houses. This might seem quite bitty, but I'm just literally racking my brain to think of the questions they'll ask you. They could ask you how a fossil fuel power station works. And actually any power station kind of works in the same way, which is that either if they're burning biomass or they're burning fossil fuels, what you're doing is you're heating water. That water turns into steam. The steam turns a turbine turns a generator, and a generator generates the electricity. So those are all the steps involved in generating electricity. Nuclear power is quite an interesting one because it's not technically renewable because you can't make more radioactive material. However, such tiny amounts are needed, it means that it's very unlikely to run out. So there is a huge potential for nuclear power. However, disadvantages include the fact that there's radioactive waste which needs to be stored very carefully, because if that escapes into water supplies, that could cause cancer. There are high decommissioning costs, and that means it's just very expensive taking the whole power station apart once it's been used for about 20 years or so. High startup costs obviously follow, so it's going to be expensive to make those factories in the first place. So the wave topic, let's try and cover as much of this as possible. There are two types of wave you need to know about: transverse and longitudinal waves. Learn the perfect definition for both. Transverse waves, vibrations occur perpendicular to the direction in which the wave is travelling. Key examples here are water waves, light waves, and any member of the EM spectrum, infrared radiation, ultraviolet, X-rays, etc. Longitudinal waves, vibrations this time occur parallel to the direction in which the wave is travelling. Your key example here is a sound wave. Be prepared to draw a longitudinal wave and notice that there are periods of rarefaction and compression. So it's like a slinky. Where it comes close together, that's compression. Where it moves further apart, that's a rarefaction. Now the wave equation states that wave speed equals wave frequency times wavelength. Wave speed measured in meters per second, frequency measured in hertz, and wavelength measured in meters. What is the frequency of the wave? Well, it's the number of waves per second. If you're labeling a wave, be prepared to draw the amplitude, which is from either the middle line to the top of the wave or to the bottom of the wave. It's not from top to bottom, that's 2 times the amplitude. The wavelength is the distance between 2 peaks or 2 troughs. The time period of a wave is the time taken to produce one wave, and it's given by the equation frequency equals 1 over time period. So let's talk about reflection. That's all to do with waves bouncing. So remember, the key thing here is to know the difference between the angle of incidence and the angle of reflection. So the wave coming in and hitting the substance is the incident ray. It bounces off, and what you find is the angle at which it bounces off, so the angle of reflection will equal the incident angle. Don't forget to label your normal line, which is a line, it's like an imaginary line drawn at 90 degrees to the boundary surface. Refraction is all about a wave changing direction when it enters a new medium, and that's due to it either slowing down or speeding up, so it's due to a change in wave speed. What you find here is that if you have a light wave entering a glass block, it will slow down and it will bend towards the normal. On exiting the block, it will speed up again and bend away from the normal, so be prepared to draw that. And also be aware of what happens when water waves move from a different depth. So when they go from deep water, you find that they're travelling really quickly and that the waves are very far apart from each other. As they enter shallower water, they slow down and the waves become closer together, and you'll actually see the wave front getting closer together. If you're struggling to remember that, just remember cars on a road. They'll be further apart when they're travelling nice and quickly, and then when you're stuck in a traffic jam and they're travelling slowly, they're basically on top of each other. What is an echo? Well, it's a reflected sound wave. Remember, they use echo sounding for working out the depth of the ocean, so they'll send down some sound waves. They'll record the time it takes for the sound wave to be transmitted and then be received again by the transmitter. You use the equation speed equals distance over time, so you know the speed of the sound wave. You've recorded the time, just make sure you halve the time, because obviously if you use the full time, then that's the time it took for the wave to hit the bottom and come back up, whereas the distance is only from the transmitter to the bottom, which is why you have to halve the time. What is ultrasound? Well, ultrasound is a longitudinal sound wave which is above the range of human hearing, so it's above 20,000 hertz. Try and be really detailed with your answers there. Infrasound is sound which is too low for the human ear to hear, so it's below 20 hertz. The last thing to do with sound waves is remember that pitch relates to the frequency of the sound wave. So the number of waves per second, the higher that number, the higher the pitch, so the squeakier the sound, like hi. Whereas amplitude, so that's the height of the wave, is all to do with the loudness of the sound. So the higher the amplitude, the louder the sound. So if we take my rubbish finger here, if I do that, can you see it has a very low amplitude, because it's very short, so that means it's a quiet sound, but because the frequency is very high, it has a high pitch, so it's a very squeaky sound. Whereas if I were to do this, we've got a much larger amplitude, so a loud sound, but because the waves are so infrequent, it's a very low sound.
Two, a microphone is connected to an oscilloscope to display a sound wave. The diagram shows the trace on the oscilloscope screen. The oscilloscope settings are: in the y direction 1 square is 1 volts, and in the x direction 1 square is 0.001 seconds. So let's make a few annotations. So that must mean that up to there is 2 volts, and this is 0.01 seconds, which means the entire wave cycle is 0.002 seconds. So how many periods are shown on the trace? And remember, the period is the time for one wave, so that's a complete wave. So there's the first wave, and you can see that repeats 3 times, which is why the answer here is 3. And what is the frequency of the sound wave? So frequency is given by f, which is 1 over the time period. So we simply do 1 divided by 0.002, which gives us a value of 500, and they've already given us the units, which is in hertz. On the grid below, sketch the trace of a sound wave with a smaller amplitude and a higher frequency than the wave shown by the dotted line. So a smaller amplitude means that it will be quieter, so our wave needs to be less high, so it needs to be much lower. High frequency means that the waves need to get closer together, so I'm going to draw it like this. And try and keep it nice and even. So I'm only going up one wave and down one wave, but because they're closer together, I've definitely drawn a higher frequency. The fact that they're lower means that it's a smaller amplitude. Let's now think about images formed in a plane mirror. So here's our plane mirror, straight line with the cross-hatching behind shows that it's a plane mirror. Remember, we have a normal line which is drawn at 90 degrees. So let's pick an object such as a flower and think about the image that will be formed by that mirror. So here is our object, so it's the actual flower that we're looking at. So how does that object actually become an image in our eye? Well, light from an object strikes the plane mirror and is reflected from the mirror surface, and then after that reflection, the light strikes the eye of the observer. But what can we actually say about that image? Well, first of all, the image is obviously the same size as the object, and it's worth making a note of everything I'm writing. And these are quite common sense points, so don't be surprised by them. Secondly, obviously the image will be the same colour as the object. The image will be the same distance behind the mirror as the object is in front. But crucially, the image will be laterally inverted, which means the left will appear on the right and the right will appear on the left. Lastly, this image will be virtual, which means that it can't appear on a screen. Now, one hard question that people do struggle is working out how to draw the image when you've been given the object, such as in this case. So here's our plane mirror. Now, the easiest thing to do here is use your ruler to draw a straight line from the object which hits the plane mirror. Then draw a second line just beneath that. And then you want to reflect that back off the mirror. So you could do it really neatly by drawing normal lines here, measuring the angle of incidence, but to be honest, you can probably get away from drawing it by eye, like I'm doing now. And then at the end of these lines, you need to draw the eye, which is actually viewing the object, so something like this is perfectly adequate. And then to finish, I'm just going to change colour. You want to take an approximation, probably use your ruler to measure this distance here so that you can draw the image behind from the same distance to make it make sense.
And then just use your ruler to draw a dotted line here. And really this distance from the object to the mirror should be the same as from the image to the mirror. And if I rub out those kind of explanation lines, really this is what your final answer should look like. Well, a convex lens is otherwise known as a converging lens, and if you know what the word converging means, it is actually just a normal English word. It means coming together. So if you've got a couple of rays and they pass through a convex or converging lens, then they'll be brought together and they'll meet behind the lens. An example of use of this is the magnifying glass. Now the focal length is the distance between the centre of the lens and its point of focus. The principal focus is the point where the parallel rays meet after they pass through the lens. And then lastly, the difference between a real image and a virtual image is that a real image can be formed on a screen and a virtual image cannot. Now, if I move on and I show you this, hopefully this will make it a bit clearer. So with the convex lens, we can see that when the parallel rays pass through it, they then come together, i.e. they converge. And the point where they converge behind the lens is called the focal point. And that's what's going on here. They're meeting. And we look at someone that's long-sighted. So this is what happens to older people. They start needing glasses to read print, like reading books or whatever. So this time you've got the parallel rays coming in. They're hitting the lens, but the lens is weakened over time. So rather than meeting on the retina here, they're meeting behind the eyeball, behind the retina. So you're going to get a very blurred image here. So instead, you need a convex or converging lens, which is actually going to cause those rays to come in, so that when they're brought onto the human lens, they meet nicely on the back of the eyeball here on the retina. So let's have a go at constructing various ray diagrams. This arrow here is supposed to be the object, this is the lens, and these are the focal points. So based on my instructions, first of all, you want to draw a horizontal line from the top of the object, use a ruler and a pencil for this, and then you want to take it through the focal point like that. Oh gosh, I really struggle on the iPad. Next step, you want to draw a diagonal line which runs from the top of the object arrow through the middle of the lens, and we'll see where it crosses. Oh, not very good, not very good. Oh, it's supposed to cross through the middle of the lens, and then where the two lines cross, that is your image. And then you need to compare it to the original object. Now, because it's underneath the line, we know that the image is inverted. If I'd drawn it accurately, the actual height of the arrow, so from here to here, compared with that, believe it or not, would have been shorter. So therefore, we know that the image formed is smaller, or we could write diminished, if you're feeling fancy, because that means smaller. And then because it's formed after the lens, then we know our image is real. If they ask you for an example of a lens which works like this, then you can talk about the eye or a camera or something like that. This one's slightly different. We can see that the object arrows now move between the focal point and the lens, so we're going to see a slightly different thing happening, but it doesn't matter, you can still use the same process. Horizontal line to the lens. Then we're going to take the line down through that focal point. And then, from here on, this is where it's a bit confusing, because if I then draw the diagonal line here, you can see those rays are never ever going to meet on the right-hand side, ever. They're just going to keep going and going and going. So what you want to do is take your ruler and carry on the lines and make them dotted. Make it nice and straight, unlike what I'm doing. Do the same here, and then eventually they'll cross, and that's actually where your image will be formed, up here. So I'm going to draw the arrow. So now let's discuss what we can see. Well, because it's the same, not the same height, but it's upright, it's the same direction as the object arrow was facing, we know that it's upright. Because the arrow is much larger, we know that it's enlarged. But because it's formed before the lens, we know it must be a virtual image. And an example of this would be the magnifying glass. And your arrows will go this way.
Dispersion's all to do with light splitting up and spreading out. So if you get white light, remember it's made up of lots of different colours. If you shine it into a prism, it will split into those colours. Remember the order of the rainbow, and that will help you with knowing what colours the light splits into. So Richard of York gave battle in vain, red, orange, yellow, green, blue, indigo, violet. Now red is refracted the least because it slows down the least. Violet is refracted the most because it was travelling the fastest and therefore slows down the most.
5. A student uses a rectangular glass block to determine the refractive index of glass. The diagram shows a ray of red light in air as it enters the glass block at P. The normal at P is shown as a dotted line, which, as we would expect, is perpendicular. Complete the diagram by drawing the ray that continues inside the block, labelling the angle of incidence and the angle of refraction, and drawing the ray that leaves the block. So use your ruler here and a pencil. So remember, as it enters the block, it enters a more dense medium, so it bends towards the normal, which is why I'm doing it here. We need to draw a second normal line down here, try and draw that more straight than I have. And then remember, as the ray leaves, it is again parallel to that ray that came in, which is why I'm doing it at this angle. Now we must label the angle of incidence and the angle of refraction. So the angle of incidence is between the normal and the incident ray. The angle of refraction, it's going to be hard to show that, that's in there. And that's between the normal and the ray that has been refracted. The student measures values for the angle of incidence I and the angle of refraction R. So I is given as 60 degrees, R is given as 34 degrees. So we need to complete the table by inserting values for sine I and sine R. So that's quite straightforward. Just put into your calculator sine 60. And when you've done that, that is 0.87 to 2 decimal places. Put into your calculator sine 34, and that is 0.56 to 2 decimal places. State the equation linking refractive index, angle of incidence, and angle of refraction. So remember, refractive index is given by n. So it's n equals sine I over sine R. So in terms of calculating refractive index, sine I is 0.87, sine R is 0.56. And when you put that into your calculator, you get a value which is 1.6 to 2 significant figures. How should the student continue the investigation to obtain a more accurate value for the refractive index of glass? So that's worth 3 marks to make 3 separate points. So the most obvious point to make is to increase the reliability. You want to repeat and calculate an average. You want to vary the angle of incidence more, so you could do 50 degrees, 70 degrees, 80 degrees. And then next you could draw a graph plotting sine I against sine R, and remember that the gradient will give you the refractive index.
The electromagnetic spectrum now, which is a little sub-topic of the waves topic. I do like this topic. Remember that it is a family of waves and they vary just in terms of their frequency and their wavelength. So let's go through those waves first of all. So starting with the longest wavelength wave, so waves which look more like this. So they have long wavelengths because remember the wavelength is the distance between 2 peaks or 2 troughs, as opposed to having short wavelengths, whereby the wavelength is this big as opposed to this big. So we're starting from the longest wavelength, that is radio waves. Then we have microwaves, infrared radiation, visible light, ultraviolet, X-rays and gamma rays. And I'll provide a link below to this video which I love. One of my tutees told me about it a couple of years ago, and I think it's sung by some South Korean guys. If you start playing it at 30 seconds, listen to the chorus through 3 times and you'll have the order nailed in your head. Otherwise, I'm sure there are lots of mnemonics that people can remember, and comment below if you know of a good one. In terms of frequency, clearly gamma rays will have the highest frequency because there's more waves per second with gamma rays because they're much closer together, whereas microwaves and radio waves will have a much lower frequency because their waves are much further apart. The key point to notice with this topic is the various uses of all of these. So we'll start with radio waves. Remember, these are used in communication. Microwaves are also used in communication, so satellite communication. They're also obviously used in cooking food. Most of us have microwaves in our kitchen. Then we have infrared radiation, and that is also used in communication, and in this case we're talking about remote controls, so communicating between the remote control that you're pointing at the TV, for example. So infrared radiation is being given off there. Remember, we met infrared radiation when we were talking about the heat topic, so conduction, convection, radiation, because infrared radiation is simply heat being given off from objects, and therefore infrared radiation is the type of radiation used in ovens. because obviously they get hot to cook our food and they are giving off infrared radiation. Visible light, as well as the usual uses, so the fact that we can see stuff with them, it's also used in optical fibres and photography. Now we're getting down to the other end of the spectrum, so where the waves start getting much closer together. The next wave we're going to be looking at is ultraviolet, so UV. Remember, these are rays that come from the sun. They have various uses, such as tanning beds, so sunbeds that will have UV rays being emitted, but also you can use it to check whether banknotes have been forged or not. So you hold it up to the UV light and you can tell if they're authentic. Then we're looking at X-rays. Obviously they're used in medicine to create images of the human body. And lastly, gamma rays. Gamma rays are used to sterilize surgical equipment because they're such high energy. They kill things effectively, so that could be killing bacteria on surgical equipment, it could be killing cancer cells. So used appropriately, they're very useful. If they're used inappropriately, they can actually cause cancer, so that's worth noticing. The way they'll ask the questions is it will say stuff like, microwaves are used in communication. Name 2 other rays also used in communication. You could have said infrared radiation, you could have said radio waves, or visible. So be aware here. What dangers are associated with infrared radiation? Well, because it's effectively heat, if it gets too hot, it can cause skin burns if you touch it. Dangers associated with ultraviolet, that will be skin cancer, because again, if used inappropriately, that can cause cancer, as well as the rays from the sun. If we're exposed to them for too long, it can cause cancer. How can we reduce danger from exposure to ultraviolet? Well, wearing sun cream, wearing sunglasses to protect our eyes, limiting our exposure time, covering up wearing clothes. To protect ourselves from X-rays, we need to limit our exposure time, hide behind LED screens, wear protective clothing, and the same is true of gamma rays. You really don't want to be exposed to these rays for too long. They could ask you what all these rays have in common, and that is that they are all transverse waves. So in all cases, vibrations occur perpendicular to the direction which the wave is travelling. Remember, that's your perfect definition of a transverse wave. They clearly all transfer energy. They may all be reflected, refracted and diffracted, so they can all bounce off objects. They can all change direction if they go through a different medium. And lastly, they travel at the same speed, which is 300 million meters per second. We start by looking back in history and look at the original structure of the atom, so we can actually understand all our findings that we know to be true today. So originally there was the Thomson plum pudding model. Now you don't need to know too much about this, but just know that a plum pudding, this was in the 1800s by the way, so you can imagine a Christmas pudding if you don't know what a plum pudding is. I don't know what one is. So a big sphere of sponge embedded with different types of fruit, and in the case of the plum pudding, those were plums. And Thomson stated that the sponge was made out of positive charge and that those plums embedded within that sphere of sponge were the electrons. Now we know that this is false because we now know the modern day structure of the atom with its nucleus and its shells with the electrons circling, and we're going to talk about the gold foil experiment to help us understand why this new atom became the accepted model. So Rutherford fired alpha particles, and we'll talk about alpha particles soon, at gold foil. Now he found that most of them passed straight through, and this was strange because really if the atom was structured like a plum pudding, there's no way these alpha particles should have passed straight through, but because they passed straight through, it told him that the atom is largely empty space, which we know to be true. Some alpha particles were deflected, and because an alpha particle is positive, it told him that they had hit something also positive and that they had been repelled, and that made him understand that the nucleus was positively charged, which we know to be true because that's where the protons are found. Lastly, very few of the alpha particles were deflected in this way, and this told him that the nucleus was very small. So do link together what he did with what findings he found out and the conclusions he drew from those findings, and that will help you score really highly. So we now have our structure of the atom. We know that it has a nucleus containing protons and neutrons. Remember, this is also known as the nucleon number, and that's just the name given to all the particles found within the nucleus. And surrounding the nucleus are the shells of electrons where the electrons orbit. So just to remind ourselves that the mass of a neutron and a proton is 1. A mass of an electron is very small, so 1 divided by 2000 or 1800, depends what your teachers taught you. And that the neutrons, because they're neutral, have no charge. Protons have a positive 1 charge and electrons have a negative 1 charge. Now looking at the periodic table, just remember that the atomic number is the number of protons and the mass number is the number of protons plus the number of neutrons. And this will become really important when we now come to look at isotopes. You've probably met isotopes in chemistry, so things like carbon-12, carbon-14. Remember that these are atoms of the same element with the same number of protons but different number of neutrons. If we look at carbon-12 and carbon-14 in the periodic table, they both have an atomic number of 6, which makes sense because they're the same element, which means that they must have the same atomic number. Their mass numbers are different though. Carbon-14 has 2 extra neutrons when compared with carbon-12. So when we look at radioactive isotopes, we're just talking about isotopes which are unstable and tend to give off radiation. So ionizing radiation may be given off an atom, and this is a random process, and it may give off alpha, beta or gamma radiation, and that's what we need to talk about now. So I'm going to start by chatting you through what alpha, beta and gamma radiation is, and then I'll show you some decay equations. So alpha radiation first of all. So what happens when alpha radiation happens is that 2 protons and 2 neutrons are lost from a particular atom, and clearly therefore you will have a new element whose atomic number, remember that's the proton number, is 2 fewer than it was before, and the mass number, because it's lost 2 protons and 2 neutrons, will have gone down by 4. With beta radiation, what's happened this time is that a neutron has turned into a proton and stayed within the nucleus of that particular atom. So because a neutron and a proton has the same charge, clearly the mass number will be unchanged, but the proton number will have gone up by 1, so you will have a new element. Now gamma radiation is very different because it's an electromagnetic wave, so you see no change in mass or atomic number. Do notice that alpha radiation is the largest, it has the largest mass because it is made up of 2 protons and 2 neutrons, and it is the most ionizing, whereas gamma is the least ionizing. And ionizing is just the ability to cause something else to become an ion, which is a charged particle. So if we compare the properties of alpha, beta and gamma, notice that alpha, as I've already said, is the most ionizing, beta is in the middle, gamma is the least ionizing. In terms of their penetrating powers, that's how easily they pass through substances. You notice that alpha is stopped by air, beta is stopped by aluminium foil, and gamma is stopped by several centimetres of lead or several metres of concrete. In terms of their range in air, alpha has a range of only about 5 to 10 centimetres, beta has a few metres range, whereas gamma has an infinite range in air.
The table shows the nature of alpha and beta particles. So alpha we know is a helium nucleus made up of 2 protons and 2 neutrons, and beta is a fast-moving electron. Explain why alpha particles and beta particles have different penetrating powers. So basically let's start by looking at the difference. So state first of all that alphas are much larger because they're made up of 2 protons and 2 neutrons, so they have a heavier mass, they have a higher charge. This means that they cause more ionization, which means they can't penetrate as far, and that's due to all the energy which has been lost as they've caused lots of ionization. And also point out that the alpha particles are more likely to collide with the atoms because they are bigger. Or you could give the converse argument for beta, so you could say they're smaller, they have less charge, they cause less ionization, they have a lower mass. So in this first alpha decay equation, let's have a look. We need to work out the new mass number and the new atomic number of thorium. So we're starting with uranium-238. That is its mass number. Well, I've just told you that you lose 2 protons and 2 neutrons in alpha decay, which means the mass number must have therefore decreased by 4, which is why its new mass number is 234. Because you've lost 2 protons, it means that the atomic number decreases by 2 to 90, and that is your answer. In the second example, I'm after the new mass number of lead, so we've lost 2 protons, 2 neutrons again, which is why the mass number will have decreased by 4 to become 212. And this time we're looking for the original atomic number or proton number of polonium. So we know that we've lost 2 protons to get to 82, which means the original atomic number must have been 2 more than 82, so the answer here is 84. In this beta equation,
we're looking at what happens to sodium. So I've already told you that in beta decay, a neutron turns into a proton and stays within the nucleus of an atom. Because of that, the mass number is unchanged. So we're going to stay having a mass number of 22. The neutron turns into a proton and stays within the nucleus, and because of that we have an increase of 1 on the atomic number, so that turns into 12, and because we've increased our atomic number we clearly have a new element, and if you look in the periodic table you'll see that the element with the atomic number of 12 is neon. So in this question we're looking for the new mass number and the new proton number again. So we have a neutron turning into a proton, meaning that the mass number is unchanged, which is why I'm going to write a 14 here. Because we've gained an extra proton, it means the atomic number will have gone up by 1, forming 7. And because you have a new atomic number, we have a new element, and that element, according to the periodic table, is nitrogen.
Now we're going to be moving on to looking at half-life and background radiation. So let's first of all state what is background radiation. And it is radiation which is always present in our surroundings. And so you may need to list several sources. So that could be cosmic rays from space. It could be radioactive rocks like granite found in Cornwall. It could be food and drink, and medical sources such as X-rays. Now what is the unit for measuring radiation? It is the becquerel, capital B, little q. And what instruments do we use to measure the level of radiation, whether that's background or not? We use the Geiger-Müller detector or counter. Do remember, if you're given a radioactive source and you need to determine its radioactivity, you must work out the level of background radiation and then subtract that from the value you get from your Geiger-Müller counter to make sure that you remove it from your calculations. So half-life, now let's define it first of all. Remember, this is the time taken for half the radioactive nuclei to decay, and you might have used coin tossing at school to help you model this. The reason why that works really well is because radioactive decay is a random process, and as is tossing the coin. And with tossing coins, you've no idea, you can't predict whether it will land on heads or tails, and it's the same with radioactive decay. You have no idea which of the radioactive atoms will decay first. In terms of using tossing a coin as a model, it does have several limitations, and this is really the number of times you can do it. I mean, realistically, probably at most about 1,000 times, whereas with radioactive decay, you're looking at millions of atoms which need to decay. And now I'm going to show you a question involving half-life, and I'll talk you through the half-life calculations because they're probably the most difficult part of this topic.
A sample of sodium-24 has an activity of 1400 becquerels. On the axis, sketch a graph to show how the activity of this sample changes over the next 40 hours. The half-life of sodium-24 is 15 hours. So at time equals 0, we're going to have an activity which is 1400. We know that the half-life is 15 hours, so look along 15 hours, half of 1400 is 700. So we need a cross there. When another 15 hours has taken place, so at 30 hours, that 700 will have halved again to 350, so we need a mark here. And now you can attempt to draw a curved line, which I'm appalling at. Oh, it's not too bad. Granite is a rock. It contains a radioactive isotope of uranium that decays very slowly. Explain how scientists can use this radioactivity to find the age of a piece of granite. So first of all, make a note that there is a known proportion of activity when the rocks are formed. This means that you can now measure the proportion of uranium now, and then you compare the activity of the original uranium's value with the activity now, and this can help you determine the number of half-lives which have elapsed, and then you calculate the age from reference to half-life. Suggests why the age of a piece of granite could not be found using uranium isotope with a half-life of 15 hours. And that's obvious because the half-life is too short. 15 hours has meant that the decay has occurred far too quickly, and so the activity now would be far too small to measure. Sodium-25 has a half-life of 1 minute. What fraction of it remains after 3 minutes? So what you have to do here is work out how many half-lives have occurred. And because it's 3 minutes and 1 goes into 3 minutes 3 times, 3 half-lives have occurred. And then all you have to do, because you're finding out a fraction, is do a half times a half times a half to find that 1/8 remains after 3 minutes. Question 3. Xenon-133 is a radioactive gas used for diagnosing lung problems. In 15 days, its activity falls to 1/8 of its original value. What is its half-life? So we need to work out how many half-lives occur to get to 1/8.
So what you need to do is, you might have to do trial and error, but you need to just do as many half-lives as you need to in order to get to 1/8, and the answer is actually going to be 3 of them. So 3 half-lives occurred in 15 days. So how long did it take for 1 half-life to occur? Well, you just need to do 15 divided by 3, and the answer is 5. So 5 days is its half-life. Question 4. The half-life of the radioactive isotope sodium-24 is 15 hours. A sample has a count rate of 240 counts per minute. Its count rate 60 hours later will be... Okay, so this time, again, we need to find out how many half-lives have occurred. So I'm going to do 60 hours divided by 15, and I see that 4 half-lives have occurred. So, therefore, after 1 half-life, 120 counts would remain. But there were 4 of them, so I'm going to times it by a half 4 times. And that is the same as 240 times answer, and that is 15 as my answer. So its count rate after 4 half-lives have occurred, so I've divided 240 by 2, or times them by half 4 times, and I have got 15 as my answer. So that's 15 counts per minute. Question 5. A radioactive isotope of silver has a half-life of 20 minutes. A sample gives a rate of 6,400 counts per second at 9 o'clock. At what time will the count rate be? About 200 counts per second. Okay, this sounds hard, but again, just use trial and error to work out how many half-lives have occurred. So I'm just going to do 6,400 times a half, and I've got 3,200, so I'm going to times it by half again. And I'm going to keep going until I get to 200. And actually what I found here is that it has taken 5 half-lives in order to get to 200 counts. So all I did was times 6,400 by a half 5 times, and I got to 200. So like I said, that means 5 half-lives have occurred, and each half-life took 20 minutes, so therefore 5 half-lives takes 100 minutes. So all you need to do now is work out what 100 minutes past 9 o'clock is, and remember there's 60 minutes an hour, so that brings us up to 10:40. That one was quite hard, but you can work it out. Like I said, just use trial and error to work out how many half-lives have occurred. Practice doing as many questions of these as possible in order to get good at answering the different types of question. Remember, when you're reading off graphs, to look at, you can read off the half-life by looking at how long it took for the counts to reduce by half, and then you need to read across to see how long that took. Take into account background radiation, because you'll see that the graph line will never actually touch the x-axis, and that's because background radiation exists. And remember that that comes from things like cosmic rays, x-rays, rocks, just general stuff really. And remember, half-life is actually the amount of time taken for half the radioactive nuclei to decay.
So, after 42 days, the activity of a sample of phosphorus-32 has decreased from 400 becquerels to 50 becquerels. What is the half-life of phosphorus-32? So we've gone from having an activity of 400 becquerels to 50, so we need to work out how many half-lives took place. So there's the first one, which would have taken us down to 200 becquerels. The second one would have taken us down to 100 becquerels. And then the third one would have taken us to 50 becquerels. So we can see here that 3 half-lives have taken place. And what was our time frame? Well, 3 half-lives must have occurred in 42 days. So then it's the simple expedient of doing 42 divided by 3 to work out how long each half-life took. And that answer is therefore 14 days.
Looking at uses of radiation. Alpha radiation is used in smoke alarms. I'm going to chat to you how this works. So you have an alpha source in a smoke alarm, which is giving off alpha particles. And what happens is those alpha particles collide with air particles in the air, and they ionize them, creating a small electric current which is picked up by the detector. Now, I've already told you that alpha's range in air is very limited. So the moment there's a fire, there's now smoke particles in the air, and they obstruct the alpha and they stop it reaching the detector. So the detector gets 0 reading, and therefore the alarm goes off. Beta radiation is used in aluminium foil thickness, so kitchen foil that you wrap your sandwiches in. So there are 2 rollers, and there's a detector either side. So you've got a source of beta, detector on the other side, and there's a certain amount that should be picked up, and if that detector reading is too low, it tells you that the aluminium foil is too thick, so the rollers press together to make the foil thinner, and so the detector can pick up the correct amount. In terms of in use in medicine, do you remember that we use radioactive sources in medicine, such as radioactive iodine, and we call this a medical tracer, and that's because it's used to diagnose things like kidney problems. So the patient takes a sample of radioactive iodine, it flows through their body, and there's a detector which picks up how much radiation there is, and you'll see a characteristic graph reading where the reading stays high, and that tells you that there's a blockage within the kidney. So they do make great diagnostic tools. Do notice some crucial properties though, and that is that you've got to have an isotope which decays into a stable product, which makes sense because you don't want it giving off radiation. It has a medium-sized half-life. You don't want it to have such a short half-life that you can't actually pick up how much there is because it's already decayed away, but you also don't want it to be so long that you're staying radioactive for many years to come, because that is dangerous, and this is because of all the dangers relating to radiation. So remember, ionizing radiation causes mutation within our cells, and mutation is the first step leading towards cancer, so it's pretty nasty stuff. We can reduce our risk and limit our exposure to radiation by wearing protective clothing, by standing behind lead shields, by using tongs to handle the radioactive material, and for using things like photographic film. You see these in little medical badges that radiographers wear, and that will show up if they've been exposed to too much radiation. Looking at use of radioactive carbon, so carbon-14 in carbon dating, so that's when you determine how old plant material is, for example. So carbon-14 is radioactive, and during a plant's lifetime, remember when it photosynthesizes, it takes in carbon dioxide. So a certain proportion of the plant will contain carbon-14. Now once it dies, clearly it won't be photosynthesizing anymore, and over time that radioactivity decreases, and by comparing the radioactivity of a sample with the radioactivity of a living version of that particular plant, you can work out how old it is. That's a very clever dating technique. So nuclear fission, let's be very specific with our definition. Remember that it is the splitting of an atomic nuclei. Do say atomic nuclei. If you don't say that, you don't get the mark. So where is this carried out? It's carried out artificially within a nuclear reactor, which means we need to add a fuel, and we tend to use uranium-235. So we have our nuclear reactor which contains uranium-235. To get the nuclear fission process underway, we have to fire a single neutron at that uranium nuclei. The uranium nuclei splits into two daughter nuclei, and I'm being very specific with my wording, and you should be using this exact wording in your exams, releasing 2 to 3 neutrons. These go off and collide with other uranium nuclei, which split, forming 2 more daughter nuclei, and 3 more neutrons are released, and before you know it, a chain reaction has been set off, and this can obviously become extremely dangerous if it isn't controlled, hence the Chernobyl disaster back in the 80s. So how do we try and improve the safety of the nuclear reactor? Well, we have several mechanisms, such as control rods. These dip into the nuclear reactor, and what they do is they absorb neutrons. So clearly, if you take away neutrons, they can't collide with any uranium, so the whole reaction slows down. You also have a moderator, and what a moderator does is that it slows the neutrons. Notice the difference. Control rods remove neutrons, moderators slow the neutrons, so they lower the kinetic energy, meaning that they collide with less energy, and therefore subsequently the reaction is made safer. You might find there's a coolant, and that's just cold water, which removes some heat from the reaction, and you'll also see that it is contained within a big lead box or concrete, and that's to improve the safety, to make sure that people that work in the nuclear reactor don't get exposed to radiation. Now, the type of energy released is going to be kinetic energy, and the kinetic energy is converted to thermal energy, which is used to heat water. That water turns into steam, and steam turns the turbines, and the turbines turn the generator, and that's how the electricity is actually produced from a nuclear reactor. There are disadvantages, although this is a great way in which we can produce electricity because you only need a very small amount of uranium in order to generate huge amounts of electricity. It is extremely dangerous. The radioactive waste remains radioactive for many years. It needs to be stored safely underground and make sure that it can't contaminate water sources which we drink. It has high decommissioning costs, and that's to do with how you actually take apart the nuclear reactor once you're done with it, and that's obviously due to the safety aspects. And it also has high startup costs, so building it in the first place will be extremely expensive.
In a nuclear reactor, uranium-235 nucleus absorbs a neutron and fission occurs. Complete the equation below that shows a typical fission reaction. Please don't find this totally overwhelming. We can work it out. So we've got uranium-235 going in, and a neutron is fired at it, leading to, I think that's barium, and krypton being produced as the smaller nuclei, and 3 neutrons given off. So basically, it's just like maths or algebra or something. You just need to make sure that whatever you started out with, which was uranium-235, everything else produced after that has to add up to 235. You can't just randomly lose matter. So effectively what you need to do is add 142 to 1 and also to 1 because that's the neutrons accounted for. And then if you add those all up and take them away from 235, you'll get an answer which is 91, and that needs to go here. And then the same below, you've got a proton number, an atomic number of 92, and we can see 0 against the neutron, so all we need to worry about is the krypton, 36. So just do 92 take 36 and you'll get an answer which is 56. B. Explain how nuclear fission can lead to a chain reaction. So for the first mark you want to say that the neutrons are released, that these are then absorbed by other uranium nuclei, and this causes further fission reactions. For another mark you could have said that neutrons are slowed by the moderator, but I don't really know why you'd think to write that particularly. C. The diagram shows a nuclear reactor. On the diagram label the control rods and the shielding. So the black things hanging down here are the control rods, and the shielding is the box on the outside which prevents excess radiation getting out. Explain why shielding is needed. You need to talk about the fact here that the reactor material or the waste is radioactive, and then for the second mark, that can lead to cancer, which is very dangerous. So that's why you obviously need to shield it and keep it away from people. And the reason why you do need shielding is because remember that radiation is very penetrating. It will pass through a huge amount of air, so you do need that concrete box around it to prevent it getting out. 12. The diagram shows the main parts of a nuclear reactor. So we've got our control rods, moderator, fuel rod, shielding, reactor vessel and coolant in. Do remember the control rods absorb excess neutrons, and the moderator removes the kinetic energy, and the moderator reduces the kinetic energy of the neutrons. The fuel rod will obviously provide the source of uranium. Anyway, draw a straight line linking each part of the reactor to its correct purpose. So I've already accidentally said what the control rod does, which is that it absorbs neutrons. I'm going to go to fuel rod because that's the next easiest one to answer. Remember that contains uranium. The moderator, I said, decreases kinetic energy, which is the same as slowing them. The reactor vessel keeps radioactive material inside the reactor. That makes sense. So the coolant transfers thermal energy. That also makes sense. Which of these is a nuclear fission product? So remember that's what is made after nuclear fission takes place, and remember nuclear fission is the splitting of the atomic nuclei which releases neutrons, which is why C is the answer here. Describe the process of nuclear fission. So a neutron is fired at the uranium-235 nucleus, and the nucleus splits, producing 2 daughter nuclei and up to 3 extra neutrons. And I've actually already said 3 or 4 marks worth of things, and you can say that kinetic energy is released. State 3 ways in which nuclear fission differs from radioactive decay. So remember, nuclear fission is a human artificial process, whereas radioactive decay occurs naturally. So start by saying that decay is a random process which occurs naturally,
whereas fission is not random, it's due to humans firing neutrons at uranium-235. You want to talk about the fact that fission produces 2 daughter nuclei, whereas decay only produces 1. And remember that alpha and beta or gamma are produced by decay, whereas in nuclear fission neither alpha or beta or gamma are released. Instead, it's simply daughter nuclei and neutrons. So let's start by looking at the solar system. So the solar system contains all the planets that you guys have heard of, and in order, starting closest to the Sun, you have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and sometimes people count Pluto, but I don't think we're supposed to count it anymore because it is too small to be counted as a planet. You saw me doing my thing of remembering this. The way I remember the order of the planets is my very easy method just speeds up naming, and that is a great mnemonic for helping you remember the order of the planets. Now, more terminology, we need to look at things like the galaxy. A galaxy is made up of billions of stars, so it's a collection of billions of stars. What is the universe? Well, the universe is made up of billions of galaxies. So we on Earth are living on a teeny tiny planet which exists in a galaxy. The galaxy you do need to know the name of, it's the Milky Way, and the Milky Way is just one of billions of galaxies which make up our universe. So yeah, it's kind of mind-boggling. I try not to think about it too much because it freaks me out.
So we know that the various objects in space are held in position due to the gravitational force. However, what does the size of that gravitational force depend upon? Firstly, the mass of an object. And this is why the gravitational force on Jupiter is much greater than that on Earth, because Jupiter is so much larger, it has a way bigger mass compared with Earth. And secondly, it's the distance between the objects. So the closer the objects are, the greater the gravitational force. So we've already touched on it, but what is that gravitational force responsible for? So it causes moons to orbit planets, planets to orbit the Sun, artificial satellites to orbit the Earth, and lastly, comets to orbit the Sun. And try and remember that comets have very elliptical orbits. So if this is the Sun, the comet's orbit is incredibly oval shaped. It's not really circular at all. We call this shape elliptical, and the comet travels fastest when it is closest to the Sun. And that's all to do with that gravitational force being stronger, which we mentioned above. When the comet's further away, such as this point over here, it will be travelling far slower. Just to touch on one more thing, so looking at moons and artificial satellites. A satellite is any object which orbits a planet or the Sun. So let's make a note here. And there are 2 categories: artificial, so ones that we put into space, and natural. And that's why I've highlighted moons, because these count as natural satellites. The next thing we need to look at is quite a complicated part of the specification, which is why does a satellite's velocity change even though it travels at a constant speed? And that kind of sounds like you're arguing with yourself, but you do need to know the difference between speed and velocity here, even though they sound like the same thing. So the real difference between speed and velocity is whether they're scalar or vector quantities. So speed is a scalar quantity, velocity is a vector quantity, and a scalar quantity just has a size or a magnitude, whereas a vector quantity has both a size, so the magnitude, and a direction, and that's key. So although you could have a car travelling along a road, we know that drawing is not my strong suit, we could say that its speed is 10 miles per hour. So you could also say, because
velocity also has a size. You could say that its velocity is 10 miles an hour. But to make it into a proper vector quantity, we need to say it is travelling at 10 miles per hour in a northerly, is that a word? Direction. Or you could say to the left. So notice, in order for it to be a vector quantity, such as in the case of velocity, it needs both a size and a direction. So going back to our initial question, which I'll write out again. So why does the satellite's velocity change even if it is travelling at a constant speed? This is because the satellite constantly changes direction, because it's moving in a circle, despite the fact that it is travelling at a constant speed. Hence, its velocity is changing. Next up, let's consider our historical models of the solar system. So in today's modern day world, we understand that we have a sun that forms the middle of our solar system, and then orbiting the sun is a collection of planets, which I'm not really going to be able to draw, but we know the planet closest to the sun is Mercury, followed by Venus, Earth, Mars. So my very easy method just speeds up naming planets, and that these are all orbiting the sun. So they go round and round in circles with their slightly elliptical orbits. Notice that they're nowhere near as elliptical as our comet. So if we were to look up, you can see how incredibly squashed that circle is for the comet. Planets have far more circular orbits. So this is the modern day model of the solar system. We call it the heliocentric model. It puts the sun in the centre of our solar system. And the man who was responsible for this was called Copernicus. Great name. This is why I think I'm not going to achieve anything in particular, because I don't have a great name. Think about Einstein, Hawking, Newton. Maybe I'm imagining that they have great names, but they sound great. Lindsay, less great. Okay, so Copernicus, the reason why he was able to come up with this model is because he actually could see what was going on. So he used telescopes to suggest the new model. And today our telescopes are even stronger, and so we've actually managed to prove that his model is correct. So historically speaking, what was the other model of the solar system? Well, it was the geocentric model. And as you might imagine, because we had no evidence to the contrary, we put ourselves as humans on Earth in the centre of the solar system. So this puts the Earth in the centre of our solar system. And the reason for this really is because we were basing all our judgments on what we could see with our naked eye. And it's because our naked eye really can't see very far, we couldn't actually see other features of our solar system, so we weren't able to observe asteroids, moons of other planets, very distant planets, so ones like Neptune. And to name someone who actually thought that the geocentric model was correct, Ptolemy, what?
Ptolemy.
And Martin tells me that Ptolemy I can't say it is the guy responsible. Is that a silent P right there? Let's now look at the origin of the universe. What a statement. Origin of the universe. And there are two theories you need to be aware of. These are the Big Bang theory and the steady state theory, and we're going to summarize these now. So the Big Bang theory is probably the one you're most familiar with, and that states that the universe is expanding after exploding suddenly in a huge explosion, which we call the Big Bang, and it means that the universe started from a very small point and that space, time and matter were created in the Big Bang. I'm going to write that down now. Whereas the steady state theory suggests that the universe has always existed, that it continues to expand, and that matter is continuously created throughout time. Notice that there is a similarity in these, in that in both theories we state that the universe is expanding, it's just the beginning of the universe is different. So let's highlight the things which are the same for both. While they both state that the universe is expanding, the difference is to do with how matter was created. So what evidence do we have for these? Well, it's split broadly into two categories. So evidence, number one is redshift. Number two is CMBR, which is cosmic microwave background radiation. So let's take each of these in turn. So redshift is quite a hard concept to understand, but basically because we think that the universe is expanding, it means that we think that distant galaxies are moving further away from us. So if we're stood on Earth over here, I'm going to pick one star in one galaxy over here, and remember the stars are luminous, they emit light which can be picked up by telescopes on Earth. Now, according to the fact that the universe is expanding and that the galaxies are moving away from us, hopefully you can see that this star would end up in a new position further away. Now, if the light being given off that original star has a wavelength of something like this, are you happy that when it moves further away that that wavelength gets stretched? So it has a longer wavelength. And if we were to look at the spectrum of colours, when you have a longer wavelength, it means that the light emitted is going to be redder. Hence why we describe this as redshift. So the light has been redshifted. So really, redshift provides evidence that the universe is expanding. So redshift can be used to support both the Big Bang theory and the steady state theory. And this is really important that you realise this. So both of these theories can be supported by redshift. Looking now at CMBR, so we've already said that this is cosmic microwave background radiation. It's detected in all directions in space. It has a constant temperature of approximately -270 degrees Celsius, and it's thought to be the remains of thermal energy from the Big Bang spread thinly across the whole universe. Now, as you might imagine, because we've mentioned Big Bang in CMBR, hopefully you can see that the Big Bang theory is supported by both redshift and CMBR. Because they do like to ask you about this. However, CMBR does not provide evidence for the steady state theory. We now need to look at the life cycle of stars, both very large stars and stars which are smaller, like our Sun. First of all, we need to understand the term nebula. Now, a nebula is just a big cloud of dust and gas, and that's the beginning of a star's life. We're going to take a small star to begin with, such as our Sun, and we're going to look at its life cycle. So to begin with that nebula, that big old ball of gas and dust needs to be brought together. How? Through gravitational pull. So it pulls together all that dust and gas, And then at that point it can start burning fuel, and the fuel in question is hydrogen, because the hydrogen nuclei come together. We call that nuclear fusion because they're fusing, and they release a huge amount of both light and thermal energy. At this point, the star is in its main sequence. It's like the adult part of its life. It will eventually run out of hydrogen fuel and it will start burning helium, and then it will swell up to form a red giant. Then at this point it turns into a white dwarf, and then when it totally runs out of fuel it will turn into a black dwarf. Large stars, so very, very large stars, have a slightly different life cycle. They start in the same place, which is that they have a nebula, so the huge dust cloud, gas cloud, will be pulled together through gravity. Then it will enter its main sequence and will start burning through its hydrogen fuel. Again, nuclear fusion is occurring. However, this time when it runs out of fuel, it will turn into a huge red supergiant, and then at this point a huge explosion occurs called a supernova. I love that word. And then dependent on the size of the star, it will either form a neutron star, and if the star is very, very massive, it will form a black hole, which you've probably heard of from films.
So how do scientists observe the universe? Well, that's through use of telescopes. We've already pointed out all the issues with using our naked eye. Honestly, really, with our eyes, we can't really see anything. So what are the 3 types of telescope you need to know about? Well, firstly, it's optical telescopes. The second is the radio telescope. And the third one is the space telescope. So let's have a look at each of these. So the optical telescope, to do with optics, so we're looking at light. So it's used to observe visible light from space. They tend to be quite small, which enables everyday people like ourselves to observe the night sky relatively easily. And for people who aren't particularly skilled in this field, we call ourselves amateurs. So it allows amateurs to view the night sky relatively easily. And crucially, they can only be used at night because they're observing light being emitted from stars in our galaxy. And their use is affected by poor weather conditions. So if it's foggy, you won't be able to see anything, or if there's a lot of light pollution. Radio telescopes, as the name suggests, are used to detect radio waves coming from space. They can be used in all weather conditions. They're very large and expensive, as you might imagine. Things which tend to be more technologically advanced do gain a lot in terms of how much they cost. Lastly then, space telescopes. Hopefully you can see we're getting more complicated. Now what you find is that objects in the universe emit electromagnetic radiation such as infrared rays, X-rays, gamma rays, and although these are often blocked by the Earth's atmosphere, they can be detected by telescopes which have been placed in space, so in orbit around the Earth. I said quite a lot there, so I'm going to write it all so you can actually see it written down. Running out of space here, so I'm just going to carry on chatting about space telescopes down here. So they can be used to observe the whole sky. They can be operated both during the day and night. Clearly they're going to be very expensive, and they're actually quite difficult to set up. And because they're in orbit in space, we can't go and fix them if they break. Only astronauts can fix them. So properly trained space people. So we've compared the three microscopes, the optical telescopes, the one that we'd use to observe the night sky, radio telescopes, and all the way up to space telescopes, which are the most technologically advanced. We've seen there are lots of disadvantages with the optical telescope. The fact that they can only be used in the night time, the fact that they're affected by poor weather conditions. But how could we improve the picture produced by an optical telescope? Well, we could use a wider aperture. That's all to do with the width of the lens. You could use a better quality lens and clearly pick the best conditions to actually use it in. Not that you do this, but if you actually went to a desert, you'd be more likely to see the sky more clearly because there'd be less light pollution. I'm going to write that here just for completeness sake. And now we're going to look at some past paper questions because this topic is quite tricky and I want you to see the sort of questions they're going to ask.
2a. Scientists no longer accept the geocentric model of the universe, but it was the accepted theory for hundreds of years. Explain why the evidence available at the time supported the geocentric model. So what is the geocentric model? Well, that's the historical but incorrect model of the solar system, which is that Earth is at the centre. And as we know to be the case today, the Sun is at the centre of our solar system and all the planets and moons orbit the Sun. So, explain why the evidence available at the time supported the geocentric model. So why would people think that Earth is at the centre? Well, firstly because they had no scientific evidence. The only evidence they had is what they could see with their eyes. And what was this evidence they could see with their eyes? Well, it showed to them that the sun and the moons appeared to move across the sky in the same direction. And due to that, people thought that them sitting on the Earth meant that they were in the middle of the solar system and that the sun and the moons were just zipping past. B. The Big Bang Theory and the Steady State Theory are two theories about the origin of the universe. The discovery of CMB led scientists to accept only one of these theories. Explain why redshift supports both of these theories, but that CMB supports only one of them. So we need to make some very basic comments, first of all, about what these two theories state and what they have in common. So you want to start by saying that both theories state that the universe is expanding. But that only the Big Bang Theory states that there was really a beginning where there was a huge explosion which sent all the matter whizzing out into space. And so if we now look at our pieces of evidence, let's first of all take redshift. Now, light from distant galaxies is redshifted, which means it has a longer wavelength, therefore indicating that these galaxies are moving further away from us. So actually, the redshift theory does indicate that the universe is expanding and therefore supports both the Big Bang Theory and the Steady State Theory. However, the CMB which is present has to provide evidence for there being a beginning, and that's why it only supports the Big Bang Theory and it is unable to support the Steady State Theory. Oh no, haven't been concise enough, falling off the edge of the page here. C part I. A star with a mass very much larger than the Sun. Okay, so what do we know about our various stars and, depending on their size, about their life cycles? So let's take a large star to begin with. So it goes through its main sequence, which is actually longer than that of a small star. And then it swells up to form a red supergiant, followed by a supernova, which is a huge explosion, and then either a black hole or a neutron star, depending on its size. However, a smaller star, such as our Sun, enters a shorter main sequence, swells up to form a red giant, but not a supergiant, and then a white dwarf, followed by a black dwarf. I do love these names. So let's have a look in these options. So a star with a mass very much larger than the Sun, has a longer main sequence than the Sun, and ends as a white dwarf. No, there's no mention of a white dwarf in my largest star notes. B, has a longer main sequence than the Sun and ends up as a black hole. Yes, that's definitely a potential. C, has a shorter main sequence. No, I already know that's wrong. D, has a shorter main sequence. No, that's wrong again, which is why the answer here has to be B. Which row has two correct statements about black holes? So a black hole is something which, it kind of really freaks me out, because basically nothing can escape it. Nothing at all. No light, nothing. Nothing. And that's why we can say that no electromagnetic radiation can escape. And if you have a look at what I have written in terms of forming a black hole, you can see that it comes from very large star going through its red supergiant phase, followed by a huge explosion. So let's have a look and see if any of these options match up with that. One thing I do want to point out is a nebula is completely wrong, because that's the very beginning of a star's life. So it wouldn't be a nebula collapsing. So that's why A is wrong. B, allows nothing to escape. Yes, that's true. A very large star collapses. Yes, that's true. C, allows nothing to escape. Yes, that's true. I've already said why it's not a nebula collapses, so C is incorrect. And then D, only allows electromagnetic radiation to escape. No, I've said even light can't escape. So that's why B is the only right answer here. You do need to know a lot about stars though. 3. Figure 2 shows some lines in the absorption spectra from 4 different galaxies, A, B, C and D, and from a laboratory source. All the spectra are aligned and to the same scale. So we've got A, B, C and D. Explain using figure 2 which galaxy is furthest away from us. Do notice that we've got this wavelength here identified, and that's because it's the only thick line, and really that's our reference point. We're going to be comparing the thick line on A, B, C and D. And the other thing to notice is which galaxy is furthest away from us, and that means is the most redshifted. Because remember, when galaxies move away from us, their wavelength effectively gets stretched like this. The wavelength is longer, and then if you look at these wavelengths along the bottom of the scale, you're looking for the longest wavelength. So which one is the most redshifted? And the longest wavelength you'll find towards the right hand side. It's the furthest right of these lines, which is why, I hope you can see this, which is why this is the answer, C, because it has been the most redshifted, and we're going to write about that now. Galaxy C is furthest away. Because it has been redshifted the most. And is therefore travelling at the fastest speed. Cool, and that is done. Part 2. In figure 2, the reference wavelength is shown at 390 nanometers. Estimate the change in reference wavelength for the light from galaxy D. So going back up, right, we have our reference wavelength, which is here. This is going to be hard for you to see. I'm just going to change colour. And it's moved to here. So you just want to use this scale to help you identify it. And if you have a look, you'll see that that is approximately 20 nanometers. But they would have accepted any answer between 19 and 25. Calculate the speed v of galaxy D. Use this equation. We've been given the speed of light, and just be really careful with your units because we've got nanometers up here, meters per second here. So actually, although they've given us the equation, we do need to just be a little bit careful. So I'm going to write the equation out. V equals c delta lambda over delta 0. C, we've been told, is 3 times 10 to the 8, so that's the speed of light. And according to this equation, we need to multiply it by delta lambda, which we've just worked out in the question above, is 20 nanometers. And then be careful, you need to convert nanometers to meters, and the way in which you do that is by doing times 10 to the minus 9. So we're going to pop that conversion in here, and then divide the whole lot by delta 0, which we know is 390 nanometers. So 390, and then we multiply that by 10 to the minus 9 again, to avoid any issues with units, and we get a final answer which is huge. It's 15,400,000 meters per second. B. Figure 3 shows a photograph of galaxy D. The photograph is taken by a student at his home. State 2 ways that the student can improve the observation techniques so that the quality of the image is improved. Some of this will be common sense, so for me that would be move your telescope to better viewing conditions. And that's actually why a lot of these satellites are found in deserts. There tends to be very little light pollution, very clear skies. So I'm just going to write, because I like this answer, move the telescope to better viewing conditions. E.g. in a dry desert. Something else you could say is use a better quality objective lens. Can you hear the ice cream man? It's not even warm. And if anyone's listened to my first chemistry video, you'll know there was a dog banging and a builder doing something else. London is so noisy. Something else you could have said is use a wider aperture camera or use longer exposure time while the telescope is locked onto a star.
So we're done. Well done for staying all this way. I'm really impressed if you managed to watch the video all in one. Don't forget about my revision guides. My perfect answer revision guides are available on my website right now at www.sciencewithhazel.co.uk. You can click on this card to buy yourself a copy of my revision guide, which makes the perfect accompaniment to these videos.